Hello. I think everything is ready. Do you see the desktop? Do you hear me? Does everything seem okay?
Yeah.
Okay, great. Thanks. Let me pop up some windows. Okay. All right. Now, let's see. We want to keep talking about these higher order functions. Uh, uh, Last time we talked about how to write map, filter, and fold. Okay, so we looked at how to write map, how to write filter, how to write fold, but we haven't really used them. So today we want to look at examples of using them. Okay, so we talked a little bit about what they do and how they work, and we derived them from their type signatures. What we did, we took their type signature and figured out what they did, how they work. But today we want to just look at examples of using them. That's like the homework assignment you have. The homework assignment you have now, the current programming assignment, you're supposed to use these functions. Okay, so yeah, in this assignment, yeah, these are the ones where I give you a type and you have to write a function that has that type. So we did those last week. Okay, and the then there's a couple recursive functions. The tricky ones are these, starting here. You have to write one-line functions using either map, reduce, or fold. So that's what we want to kind of look at today. What do we mean by writing a one-line function that uses map, filter, and fold? So I'll look at some examples like this. Okay. Now, what I have on my computer, we'll see, I haven't put it up on the website yet, but I have this. I have a big list of higher order function problems. Okay. So this is I made this list a long time ago. It's just a long list of problems, and we're going to look at some of the problems. I'm going to put this whole list up on the website. There are just a lot of good practice problems. Okay, so like first, let's start off with these. Like here, what does this do? Okay, so let's look at what this thing does. It's map. So map apply. Let's see if we go back here where we wrote map. You know, what does map do? The idea of map is it takes in a function and a list. See, it takes a function from A's to B's, a list of A's, and it produces a list of B's. So the idea is it should take this function, apply it to each item of this list to get an item in that list. And that's what it ends up doing. It takes the input list, takes the head of it, applies the function to the head of the list, and puts that on the recursive call to the rest of the list. Okay, so look at an example then. What does this do? This applies the length function to each item of the list. Now the list is a list of lists. So it's going to compute the length of that list, then the length of that list. Because it's going to do is it's going to take off, it's going to peel off one item from this list. The list, that's the first item in the list, and apply that function to that item, then apply that function to each item. So the answer is going to give us 3, 1, 4, 2. Okay, so let's just check. Let's put that in ML. Okay, so 3, 1, 4, 2. Now here I'm doing kind of the easy thing. I'm giving you a line of code that uses map and asking what does it do. Then we're going to get to the harder thing where I say write a line of code that uses map to do something. Okay, so first let's just practice reading things that have map, and then we'll look at writing things that have map and folds. Okay, so now what would this do? Very similar. This is going to map. Oh, this is supposed to be, okay, it's going to map the head function onto each item of this list. In this case, the list is same list as before, and it's going to map this function to that item and get 2. then map this to that item and get 4, then map this to that item and get 6, okay? So can check. So we should get the answer 2, 4, 6, 4. Okay, 2, 4, 6, 4. And then this one's going to map tail. Okay, now when it maps tail to this, it'll give us a list. So the answer this time is going to be another list of lists. The tail of this is 3, 5. The tail of this is the empty list. The tail of this is 7, 4, 3. The tail of this is 4. So yeah, map is actually pretty straightforward. Reading maps are pretty easy. Reading map commands is easy. Sometimes writing things with map is a little bit tricky, but reading it is pretty easy. Except this one. Here's something that's a little bit tricky. Okay, notice it's got map, map. Okay, now read this real carefully. I'm mapping something on a list. Okay, the list is a list of lists. Okay, so the something I map on the list should take that item and do something with it. So the thing I map on here should be something that takes a list. So what am I mapping onto here? I'm mapping the map of that function. Okay, so I'm mapping the map of this function onto this list. So that'll take the first item in the list and map the add3 function to it. Okay, so it's a nested mapping. This is very close to what in a traditional language you think of as a nested for loops. Because what does map do? Map iterates through this list. But then inside the map is another map. That map iterates through this list. The inner map maps through that, iterates through that list and adds 3 to 2, 3 to 3, 3 to 5. Then when that map is done, you go back to the outer map. Then the outer map will step to this list, and then it'll map this function on that list. So then it'll map adding 3 to 4. Then it'll be done, the inner map will be done, and then you'll iterate to the next item in this list, and then map will map this function onto that. So the result would be a list of lists where every number has been incremented by 3. It's nested maps. Okay, and if we look real carefully, we can see that 2, 3, 5 became 5, 6, 8. Add 3 to 2, add 3 to 3, add 3 to 5. Okay, then add 3 to 4, get the 7. Okay, so nested maps. And the parentheses are important. Parentheses help you map maps something onto a list. Okay, and then if I take away these parentheses, then the something would be really messed up. I would be mapping map onto a list. See, and that wouldn't make sense. So I need the parentheses here to say that this is the thing that map is mapping. So I group it together. Map is mapping the map of that function. Now remember, map takes in 3 things, but here map is only given one of the 3. I'm sorry, map takes in 2 things. Map takes in a function and a list. Okay, so this map takes in a function and a list. Now what about this map? It seems to be only given a function, but this map is being mapped on the items in this list. So this map will get its second parameter when this map is mapped onto this guy here. It's a little bit, this is the tricky part. See, this map is only being given one of its parameters. It'll get its second parameter when it's mapped onto here. Then it'll get its other parameter. Then it'll get its second parameter when this guy is mapped onto here. Okay, so this is a real interesting example of what we call partial application. Map takes 2 parameters. I only gave it one of them here, the function. And it gets the second parameter when this thing is mapped onto that list. Here's another example that's real similar. Now I'm just mapping the squaring function. So I'm mapping the map of the squaring function onto a list of lists, okay? And so the outer map will step through the outer list. So this map will first take this first item of the outer list. Then it'll take that item and map this function onto that list. So I'll map the squaring function onto 2, 3, 5. Then after this has been acted on this list, then the outer map will step to the next list and then remap this function on that second list and get 16. Then this map will step to the next list and map this map on that list. So essentially, it literally amounts to nested for loops, the concept of nested for loops, but written all compact. If you turn this into Java, you'd end up writing about 10 lines of code because you would have to literally write this in terms of nested for loops that were iterating through a list of lists. Okay, and this would end up just being much more complicated. ML has this really compact way of thinking about these things. So this kind of complex data structure, a list of lists, I can iterate through the outer list and iterate through the inner list with a map of a map. Okay, so this is a trickier map to read than this is a real simple idea. Map a function on a list. Okay. In fact, I can even do a more simple map, like, because these are already lists of lists. So a real simple map would be like the inner ones that are being done before inside there. So map the function x goes to x plus 2. Map that function on the list 1, 3, 6. Okay. So there's a real simple map. That's the most basic map. Map a function on a list. Okay. So that's the most simple kind of map of numbers. This is just a little bit trickier because this is a function that takes in a list. So if I'm going to map this function onto a list, it needs to be a list of lists because this function itself wants a list. Same with head and tail. So this is mapping a function on a list of lists. So this is mapping a function just on a list. Another simple example like this one would be map string dot size on a list of strings. Okay, so the function is the thing that computes the length of a string. I map it on a list of strings. So that's a simple one. There's nothing really tricky there. Well, in a way it is. I mean, that's a list of lists because each string is a list of characters, but we don't really even think of it that way. We just think that this is just like, it's more or less like this one up here. That function consumes a string. Then that function consumes the next string. So maps this function, moves this function along the list. One way to think about it is that iterates through the list and applies the function to this one, then this one, this one, then that one. Okay, so in this case, it would just be real simple. Oops, what did I do wrong? Oh, that wasn't an error message. That's the auto loading. Then after it's done the auto loading, the result was 4, 3, 5, 4. 4, 3, 5, 4. The links. Okay, so there's some simple examples. Okay, all right. So those are map. Map is a pretty straightforward one. Okay. Now here's another kind of problem. We'll do a couple of these. Thinking hard about how to read functions in ML. Okay. That's a function of 3 parameters, x, y, z. Okay, it does a simple math formula with them. 2 times x plus 3 times y plus 4 times z. Now, the tricky part is to start reading weird things like, what does it mean to take f of 5? Well, in ML, that's what we call partial application. That gives f the 5, and later on, it'll get the y and the z. So that would be the function 2 times 5 is 10, 10 plus 3y plus 4z. So the function, now notice that the result is given to g1. So g1 is a function of y and z that adds 10 to 3 times y plus 4 times z. Okay, so this is kind of a quirky thing to do. G is a kind of if we think of it as G is a special case of f. You've given f a little bit of one of its parameters. You've given f, you've specialized f to be the version of f that always has x equal 5. Okay, so now you've got a specialized version of f, and we're going to call it g1. It's already got the first parameter, and it's waiting for the other two. Okay, so now, that's exactly what we did here with map. This was a specialized version of map. It got one of its parameters, the thing it's supposed to map, and it was waiting for the other parameter, what it maps it to. So in a sense, this is a specialized version of map, the thing that maps the squaring function. So that is the thing that maps the squaring function, and it's being used over and over again. So this is the function f specialized to the version that already has got x. Okay, so if you go over here and give that to ML, you can kind of see it do this. Okay, so there's f. Now let's ask what's defined as g1. Okay, g1 is a function of two inputs. Now we know that over here, that would be the y and the z. Okay, and what does g1 do? Well, you can't ask for, unfortunately over here, you can't ask what the formula for g1 is. You can only ask for its type. So, there's no way to ask over here, what does g1 do? I mean, I know over here, I know what g1's type is, but I can apply g1 to say 2, 1. Oh, I'm sorry, it's g1. G1 applied to 2, 1 gives me 20. Then I can just go over here and check. Well, that was 2 and 1. Okay, so that's 6 plus 4 is 10, but this was already 10. 10 plus 10 is 20. Okay, so G1 is the name I'm giving to this special version of f that's been given one of its parameters already. Okay, all right, now here's something kind of the similar. These two are almost the same thing. The second line is actually a more verbose way of defining this. If I give f5, it still needs a u and a v. So here I write f of 5 with an unknown u and an unknown v, and those are the parameters to g2. So function, notice that this used val. G1 is the result of this. G2 is I'm defining a new function. G2 is a function of u and v that you get by taking 5 u and v into f. G2 and G1 are the exact same thing. Okay, they're literally two ways of saying the same thing. This is the elegant way of saying it. This is the more verbose way of saying it. I want to specialize f to the version that's got 5 in the first variable, and then there's going to be 2 more variables. So here I say function G2 takes 2 parameters. I take those 2 parameters and plug them into f after f's been given 5. That's exactly what this one does. But this one just does it more, essentially with less code in a more compact way, saying that G1 is the result of giving f just 5. If you give f just 5, well, G1's a function of the y and the z. Okay. Now, G3 actually isn't the same as G1 because G3 specializes f, but G3 takes the u and makes it the last variable of f and takes the v and makes it the first variable of f. Okay, so G3 is not the same as G2 is G1, but G3 is a little bit different. And then G5 really looks different. G5 takes the 5 and puts it into the last variable of f. It puts the 5 into the z and leaves f needing 2 more variables. Okay, So G5 takes in two variables. It gives those two variables as the first two to F, and then gives F a 5. Okay, so if you wrote them out as, you can write out over here what the results are. If you use like a more traditional math notation, you'd say that G1 of, say, oh, I'm sorry, G1 of two variables. G1 is a function of two variables. I can call them anything I want. I'll use U and V. G1 is a function of U and V, and it's 10 plus 3 times U plus 5 times V. Okay. G2 is exactly the same thing. Because G2 takes in a U and a V. It puts 5 into F, which gives me the 10. Then it plugs the U into the Y and the V into the Z. Okay, so it gives that exact same thing. But now this one's going to be a little bit different. G3 of a U and a V is, okay, 5 goes into the X, so I get, oops, so I get 10 here. The V, which was this second variable, the V goes into where Y is, so that's plus 3 times V. Let me make these easier to read. Okay, now it's plus 3 times V plus, now the second, the first variable U went into the third variable of F. So that went into the Z slot. So that's 5. Oh, I'm sorry, these were 4s over here. Okay, that's 4 times U. Okay, a little bit weird. Okay, yeah, it might seem like I'm arbitrarily playing games just to make things tricky, and that's not really the case at all. There's lots of code written like this. When you start looking at, if you start looking at JavaScript libraries and look at what people are doing, if you started actually looking at the code of how the Vue library is written or the Angular library is written, you start looking at how people really write JavaScript code, you'll see lots of this kind of stuff. People are more and more JavaScript, especially, is being written in this kind of functional style. And the code is, it looks like this. This is good practice in thinking about the kinds of ways that people are actually starting to code in more abstract ways. They build up, like this is real simple, just little math formulas. But the kinds of things I'm doing here are the kinds of things they're doing on a bigger scale, but it's the same kind of thing, which makes it even harder to read because they're doing these tricky kind of manipulations on a grander scale. So this is a good place to start with trying to understand, what is this thing doing here? Okay. Now let's do one more of these. What does G4 do? G4 in math notation takes in two variables. Okay, let's figure out what the formula is. G4 is going to be F of U. Well, U goes into there, so that'll be 2 times U plus. Then the 5 will go into there, so that would be 15 plus. Then the V is the third parameter of F, so it goes 4 times V. No, normally usually wouldn't write it that way. If you were actually writing this in math notation, you'd probably put the 15 out in front then and write it like that. Okay, so there's what G4 looks like. And you can kind of go through, and then you can do G5 too. You just like carefully read across what it does. Its first parameter goes into the first parameter of F. Its second parameter goes into the second parameter F, and then the third parameter F is a 5. Now look at G6. G6 now is back more like G1, it's a partial application. G6 is the result of giving F two numbers. If you give F two numbers, it's going to be left with the third parameter. So G6 is a function of W. Why did I choose W? Because I can give it any name I want. It's a function of one input. G6 takes one number in because it needs the third number that F needed. Now, the third number of F was a Z, but I don't have to use that variable. The name of the variable is unimportant. So I'm going to say that G of 6 takes in a number called W. Okay, what's it going to do with the W? Well, that W will be, see, this is still waiting for its third input. So that W goes in here in the Z slot. So I'll get 4 times W. But the 5 and the 4 were already consumed by F. So I had a 5 here and a 4 here. So that's 10 plus 12. So that's 22 plus 4W. Okay. So G6 is the function 22 plus 4W. Whatever, or whatever, you can call this the letter A if you want. G6 of its input is 22 plus 4 times its input. Notice that there is no input specified here. The input to G6 is what's left over when you give F two inputs. It's called Z here, but that doesn't mean I have to call it Z down here. I mean, here G just takes in one input. If you go over here and give this to ML, see, this is going to tell you that G takes in an int. See, it doesn't tell you what you can give it any name you want. It tells you G6 is a function that takes in an int and gives you out an int. Okay, if I give it the number 1, I should get back 26. So G6 of 1 is 26, okay, because it's 22 plus 4 times its input number. If I give it the number 2, okay, I should get out 22 plus 8 will be 30. So I get out 30, okay? So I can figure out what it does. It's not obvious what this thing does. It takes a little bit of work. Notice how this is a val, but this is a function. This is a function because I'm saying the function of those parameters. This one's a val because it's the result returned by calling F with only 2 of its parameters. So see, this is a return value from calling F with only 2 of its parameters. This is defining a function. You can tell the difference because this says this name with those parameters is the result of calling this function with 3 parameters. Okay, so I give it the U and the V, and I give it an extra constant. Here, I'm just saying, call F with those parameters and get back a return value and let G be a name for it. But the return value is a function. It's a function of the missing parameter. It's a function of this last parameter. Okay, so notice if you go down here, some of these are functions and some of them are values. This one's a function because I'm saying that G7 of U. Here I'm saying G8 of U. But here I'm saying val, G10 is the result of giving G2 one of its parameters. So once you go back up here to what G2 is, and then you say give G2 5 for the view, and then so that becomes a function of the second parameter only. Okay, so you have to work your way down this list real carefully. And the goal here is to actually, the answer really is to give these formulas here, because ML will tell you what the type of these is, but the real question is what formula do each of these functions really do? So these problems really ask you to figure out what is the actual formula that each of these functions is really computing. Okay, all right, see, practice in reading new kinds of code. But what this is practice is thinking about partial applications and the difference between defining a function and getting the return value for a function. Okay, see, I'm not defining a function here because there's no parameter. I'm just getting the return value from that function call. Okay, it's a little bit tricky to read because that's a function definition that's a function call. But this is a function call, but it's a function call in the body of a function definition. So this function call is not made until you call that function. This function call is made on that line. Notice that that's a real subtle difference. This function is, when I execute this line of code, I'm not calling f. F is now in the body of the function g5. I didn't call f. I'm not calling f until I say g5 of some parameters like 2, 3. When I call g5, I'll pass 2 and 3 to these parameters and then call f. On the other hand, this is a call to f in that line of code. This line of code calls f. Right now, I just called f, got back a result, and made g6 the name of that result. In a sense, that's really hard to figure out, that this is not calling f yet because it's defining a function. So you're just saying that the meaning of this function is you will call f when you call this function. Here I'm saying, call this function and assign its return value to this. But if you look over here, it sure is hard to tell the difference between those. If I just indent that a little bit, okay, that's a function call. That's not a function call. Okay, really weird. This is not a function call because it's part of a function definition. So it's got the word fun on the left. This is a function call because it's the return value that's assigned to that guy. Okay, so if you line these up and look at it from that point of view, it's really weird to think that, like, if I line all these up, some of these are really function calls and some of them aren't. Okay, the ones that have fun in front, these are not function calls yet. You're putting the function in the body of another function. So this function isn't called until you call that function. This function isn't called until you call that function. Okay, but this one, that's a function call. And then the result of it is assigned to that variable. But the result of this function is a function. So this function returned a function. And this style of thinking takes some getting used to. Yeah, this style of thinking really can take some real getting used to. Okay. Okay. So that's one kind of example of tricky thinking with functions. Okay. Now let's look at a similar kind of problem. Here I'm doing games with anonymous functions. Okay. Like, take this example here. Instead of saying, okay, let's look at that line of code by itself. Here's how you would usually think about it. I would say, I have a function called h, and h takes in one parameter, and what h does is take 3 times its input and adds 2 to it. Okay, and then I want to say, what's h of 5? Okay, these two lines of code are that. The function x, the function of x that returns 3x plus 2 is being called with that input. See, if you think about it, what I did is I took this okay, here's another way to write this. Val h. H is a name for something. What's it a name of? The function that takes in x and gives me out 3 times x plus 2. And now I want to take h of 5. Okay. These two lines are equivalent to these two lines, which are equivalent to this one line. Here I'm using the notation that says I'm defining the function h of x. Here I'm saying I'm defining the variable, which is the function of x that returns 3x plus 2. Here I'm saying the function h, which takes in x, is 3x plus 2. And then here I'm saying apply h to 5, and here I'm saying apply h to 5. Now, okay, now then, see, there's the function, apply to 5. Okay, 3 ways of saying the same thing. Okay, that's the function, and it's being called immediately here. JavaScript does this stuff all the time. And in JavaScript, it's done so often, it's got its own acronym. See if I can remember it. Oh, what's it? I can't remember the acronym. Yeah, immediately invoked function. See, I just started typing. I typed JavaScript IMM, and I get back JavaScript immediately invoked function. They're called IIFEs. Because what am I doing? I'm immediately invoking the function I'm defining right here. See, I'm defining the function and immediately calling it all in one line. This pattern is used so often in JavaScript that they gave it a name. It's IIFE, immediately invoked function expression. I forgot the E at the end, IIEFE. And see the weird notation? From here up to here is the function. Then this is the function call. Now in ML, I don't need parentheses to make the function call. So there's the function with parentheses around it. And the JavaScript does the same. There's the function with parentheses around it. And then there's the call to the function, and then a semicolon at the end. And if the function took a parameter, the parameter would go inside there. Okay, see, this is a void function, so it doesn't take a parameter there. But that's how they write the pattern. Okay, and that's what I'm doing here. The function of something immediately evoked with an input. Okay, so this is not silly. This way of thinking is ubiquitous. I mean, and JavaScript does it all over the place, and they even gave it a name, so people go, oh yeah, we're using IIFEs here. Yeah, we're using the IIFE pattern here, and that's what people say. They think of it as a design pattern. So this is a design pattern to them. It's also self-executing anonymous function. That's it's an anonymous function. See, now what I did over here is I didn't make it anonymous. I gave it a name. See, here I was naming the function, then calling it. Here I named the function a different way, then call it. Here, there's the anonymous function immediately invoked. So they also refer to it as self-executing anonymous functions. Okay, and try reading these examples. They get pretty hairy. You'll see some JavaScript stuff that can be really tough to read because it's using this little pattern here. And they do it all the time. They bury these in, they'll bury one of these little IIFEs in the middle of some larger thing. So this could be a line of code by itself, or it could be buried in some other bigger line of code. You see these buried inside of objects a lot of times. So in JavaScript, this kind of thing gets buried inside of an object. This idea came straight out of ML. I mean, it was the JavaScript people adopted it from this style of programming over here. Here I'm doing it with math formulas to try to make it a little bit more digestible. So here it's done with math formulas. In JavaScript, it's usually done with objects, and a lot of times it's done with callback functions and event handlers. A lot of callback functions and event handlers make use of this stuff here. And they can write really inscrutable code that you can really have. If you think this stuff is tricky to read, wait till you look at some people's JavaScript where they're doing these kinds of things. Okay, so start now. Now go here to some more complicated ones. This is a function of two variables because it takes in one variable and then asks for another variable, and then it gives me back 3x plus y. And then there's the two parameters. So that's 5 into x and 2 into y. So that's just going to give me 3 times 5 plus 2. Okay. Okay. Now here's a trickier one. This one's really, well, actually, this one just, okay. What this one does is it takes a function of one variable, applies 5 to it and gets back a number, and then just applies the result of that function into another function. So this is a chaining of 2 functions. So this is 2 chained IIFEs. It's an IIFE applied to an IIFE. It's a immediately invoked function applied to the result of an immediately invoked function. Okay, so it's taking the 5, plugging it into the 3x and getting back 15. So this comes out as 15, then the 15 is put into here to get 15 plus 2 is 7. So the result of this is going to be 17. If you go over here and just punch it into ML, oops, $17, okay? Okay, now let's try to read this one, okay? This one's a little bit, this is the one that's really kind of weird. Look at the grouping. Notice that there is a thing from there to there with parentheses around it. Then there's a space. Then there's a thing from there to there. Then there's a space and there's a thing. So there's 3 things on that line. 3 things. If you want, you can put a little bit more space between them so you can space them apart. Okay. Notice that when you have weird problems like these, you have to attack them in a very kind of rigorous way. And usually it's, you first just break it up into how many things it is. Like this was 3 things too. There was this thing, and then this number and this number. And here there were 2 things. There was this thing, which is a function applied to this parameter. Okay. Now, whenever you have a thing with a space and another thing, that means function call. The thing on the left has got to be a function, and the thing on the right is its parameter. So this is a function. All that's a function being applied to 5. All this is a function being applied to 5. So this is a function that takes as its input this function. So this is a function input to a function. This function goes into the X slot. So X is a function. On the left there, X is a function. And I know that because this function takes in one thing, and there's the thing being fed into it. The thing being fed into it is a function. What's this guy going to do with that function? It's going to call it here and call it here. It's going to call that function 2 times. It's going to take that function and feed it y. Then the result of feeding that function y is going to be fed back into f again. So it's going to call that function on the result of calling that function on y. Well, where did y come from? Well, that's another function value here. Okay. Now, here's how I would work this out. If I, this function here's how you sort all this out. You do it in steps. This is called substitution. This function here is the x. So it's going to go here and here. And now I don't need this input here. This is gone. I've substituted. I did something wrong there. I didn't want to cut that out. I just wanted to copy it. I accidentally cut it when I wanted to copy it. So I want that still in here. Oh, now I've got it messed up. I shouldn't be using Notepad. Notepad doesn't have undos. I forgot that I opened this thing in Notepad. Notepad doesn't have undo. It's just the stupidest editor in the world to use. I shouldn't have been using it. So now I can't go back to where I was because Notepad doesn't have undos. Okay. Let me get this problem from my, I have a, well, let's see. Did I leave it on the, let's see. No, I pulled it out of there. So let me go get the, there's the example we're working on. Let me get it. Okay, there's the example we're working on. I took this guy and put it into here and here because f was a function. There's the body of f. I'm just going to substitute the parameter into the body. So I'm going to substitute the parameter into the body of the function. Okay, so let me do that over again. Okay, so make a copy of the function. Make a copy. Okay, take this and substitute it into this parameter here. So I substitute it into there. I substitute it into there, and I substitute it into there. Okay. Now, since I've called that function, I don't need that parentheses, and I don't need that. Okay. I've done one substitution. I substituted this into here. Okay. Now I've got a line of code with two things on it. There's a thing, and there's its input parameter. So this is a function of y with 4 as the input parameter. So I'm going to do a substitution again. Okay, I'm going to take this, make a copy of it, and I'm going to plug 4 into y. So 4 will go into y there. Okay. Now since I plugged 4 into y, I don't need the function call here. Okay. Now let's see if I may have messed up the parentheses. No. Now I've got a function applied to this thing, but this thing is a function applied to 4. Okay, so if I apply this thing to 4, it's just 3 times 4, which is 12. So this thing is 12. Then 12 is going to go into here, and I got 3 times 12 is 36. Okay, so the thing I started with, this guy, should be 36. So let's just check. Let's take the original, go to ML, 36. Okay. See, I unraveled it step by step. Really tricky. This is referred to as substitution. This it sort of goes back to what you learned in elementary school. If you go back to elementary school ideas and you ask, what is, if you have a function f of x is equal to 3 times x plus 2 times x squared, then what's f of 5? Well, what do? You substitute 5 into here and here. So you substitute 5 into there. 5 times 5 is 25. 2 times 25 is 50 plus 15. You substitute that into there. Well, that's what I did here, but with a much more elaborate example. I was substituting functions. I was substituting whole functions in for, I was substituting a whole function here in for that parameter x there. Okay, so I unraveled this thing by doing one substitution after another substitution after another substitution till I could get down to the final result. Okay, it's practice in weird thinking, but it's not as weird thinking as you might think. There's more and more people, like I keep hammering away at this, there's more and more people writing code that works this way. Okay, there's more and more code being written that kind of works this way. Now let me get out of Notepad. That was really, I shouldn't be doing that in Notepad. Okay, now I'm more comfortable. Okay, now I'm in Notepad. Okay, now let's do some, so I'm not going to continue. There's more of these, but let's switch to what folds look like. Now, this problem here is a lot like the first one, where it just said, what does map do? Okay, so now let's do a little bit harder one. What do folds do? Okay, what does a fold do? Okay, the key to fold is one of the things we talked about, actually it was a few days ago. When you fold a function and an initial value on a list, you read it this way. It's really saying, it's building up this chain of function calls. What it's doing is it's taking that number, putting it in, well, actually think of it down here. See, it's taking the last number in the list and applying it to f with a z. So it's taking this guy and this guy from the end. See, this is fold R, so it starts at the right end of the list. Starts with the right end of the list, and it plugs that number and that number into f. Okay, so that's that. Now that gives you an answer. That answer now is paired with this guy in f. That gives you another answer. That answer is paired with this one in f. So see, you start, this is called the initial value. You use it on the right of x4 in f, and that gives you an answer. You use that answer to the right of x3, then you use that answer to the right of x2, then you use that answer to the right of x1, and then you use that answer to the right of x0. Okay. You can also think of it as written this way here with this operator representing what the function is, like plus or minus. So it's x4 operated on by z, then that result on the right of x3, then that result on the right of x2. That, okay, and that's why it's called fold R. Each previous value is used on the right of the next value. So you start with z all the way on the right of x4. So z is on the right of x4. Compute with f, one step. Then you put that on the right of x3. Okay, then that, compute that next step, then get that result, put it on the right of x2, compute that result. And it's called fold because as you do these calculations, this thing kind of folds in on itself and collapses to a single number. You know, people call it, they called it, it used to be called reduce. You're reducing a list to a single number. But then at some point they started calling it fold instead of reduce. And you still, if you look in different languages, about half the languages in the world that have this function call it reduce, and about half call it fold. So I think JavaScript calls it reduce, I think. ML calls it fold. Yeah, so it reduces a list to a single value, or you can think of it as it collapses the list on itself from right. In this case, fold R collapses it from right to left. Fold L will do it the other way around. Fold L takes Z and matches it with X0, then takes that result and matches it with X1. So another way to think of it is this fold L works from left to right. Fold R works from right to left. They both take in a function of two variables, a seed value or initial value, and then a list to fold. Okay, now go over here and look at an example of using it. So what this is going to do, so work it out the long way. It's a fold R, so 10 starts off here on the right. So there's the initial value. The operator is addition. So 10 is going to be added on to the 5. That's the first step. We put 10 to the right of 5 and do the operator on it. Then that's going to be on the right of adding to 4. Then that result is going to be on the right of adding to 3. Then that's going to be on the right of adding to 2. Okay. And I need to keep, I keep regrouping it. Now, in the case of plus, the grouping doesn't matter. But when you do more tricky operations, if you don't do the grouping, you lose track of what you're doing. So then the last step would be 1 plus all that. Okay. So it's just adding up. Now, notice that in this case, it's real easy. It's adding up the list, starting with the 10 as the initial value. So it's 10 plus 5 plus 4 plus 3 plus 2 plus 1. Okay. So that's pretty straightforward. So it just added up the list. Okay. Now I got that by thinking of what fold does by this, essentially this picture here. Or some people like to think of it using the F notation. Some people like to think of it using this operator notation. So you can think of, see, in our case, the F is really a plus operator. And a lot of times when you're using fold, you're really using it with an operator. Though sometimes you use fold with an actual function. Okay, so you can think of it as in this function notation, or you could think of it in this operator notation. And you go back and forth. If fold's called with an operator, it's more natural to think of it using operator notation. Down here, fold is called with a function. Okay, so it's called here with a function, an anonymous function, a function that doesn't have a name. There's the function that's being folded on this list. Okay, so this one's kind of messy. There's the function, doesn't even have a name, and that function is being used in this folding operation. Okay, now this one does a fold L with the same operator. Okay, now fold L, what will we do here? We would start with the 1, start on that end of the list. Okay, so we would have, now ML's weird. The fold L and ML, here's what fold L should do. Fold L should be the mirror image of fold R. So this one should do the following. Start with 10, add it to 1. That's my initial result. Then take that and add it to 2. Okay. I'm going to work from left to right. After adding 10 to 1, I take that result, add it to 2, then take that result, add it to 3. Now, this is not what ML does. This is what Haskell does, and almost every other language in the world does, but ML's got a really quirky sense of what fold L should do. So this is how almost everybody thinks of it, like that. Fold L is the mirror image of fold R. Fold R worked from right to left. It started on the right and worked to the left. Fold L starts on the left and works to the right. So this initial value is on the extreme left. Then you add 1 to it, which is the first time in the list. Then add 2 to the result, then add 3 to the result, add 4 to the result, add 5 to the result. Okay. Everyone but ML thinks of it that way. Okay. But ML's got kind of a quirkiness to its fold L. ML does it it works from left to right. So it's going to start with the 1 first. And it's going to add it to the 10. Okay. And it's going to put it over. It's going to write it kind of like, see if I can remember. It's going to do, I think it does 10 plus 1. See if I can. Notice that here it started with 5 plus 10, but 10 is on the right. Here it's going to start with 10 plus 1. 10 is on the left, and I started with the leftmost number. Okay. Now let's see, or is that the let me look at the definition of ML's F fold L is confusing as heck. They really, for a weird reason, they kind of goofed it up. See, even though it's fold L, the initial value is on the right. Okay, so this would be 1 plus 10, not 10 plus 1. Okay, so it's 1 plus 10. Okay, the initial value is on the right. Okay, so here, so see, the initial value is on the right, and you add the first number to it, then that's on the, then you take the next number and add it on to that. Then you take the next number, but the next number is coming, but I'm reading from left to right, not reading from right to left. So I kind of do it the same. I guess if you think about it, it is in a way symmetric to fold R. Fold R works from this way to the left. Fold L works from this way to the right. But you start over here on this end with this end. Okay. So I start here with 1 plus 10, then that results added to 2, then that results added to 3, then 4 is added on to that result. And then 5 is added on to that result. Okay, so that's what fold. Okay, so this is fold L. I'm sorry, this one's fold R. This one is ML's fold L, and this one everyone else's. This is fold L for everyone but ML, would be this one down here. Okay, notice that this fold R and ML's fold L do look kind of alike, but here you're working from right to left, you know, these numbers. Here you're working from left to right, and these numbers written from right to left. See, it's just kind of weird. You know, so you're reading this list going across this way, but you put them in this list going backwards. See, it's the reverse of what's over here. So it looks like fold R, but with these numbers in reverse. Whereas everybody else's fold L is the symmetric thing to what fold R does. Fold R started on the right with the 10 on the right and then added the numbers over here. Fold L would put the 10 on the left and start adding the numbers off to the right. Okay, I don't have a real good explanation why ML came up with a different way of doing fold L than the rest of the world. Okay, turns out to not be a huge difference. Yeah, their fold L is just as useful as everybody else's fold L, but it's a little bit quirky to get used to it. And if you actually start using this stuff like in JavaScript, you have to be real careful to figure out which fold L people are using. Everybody uses the same fold R. There's only one fold R. Actually, there are 2 fold Rs, but nobody else uses the other one. There's actually 2 fold Rs, but everybody uses this one. There's 2 fold Ls. ML uses this one, and everybody else uses this one for fold L. Okay. the way to think about fold L is always to go back to these little formulas here. You know, to think fold L and fold R, take a list and build up this symbol here. Or, that's using operator notation. This is using function notation. Okay. There's also a tree notation for it. You can draw a tree. This expression here is this tree. Okay. Okay. So you can think of these things in terms of trees. See, there's the tree for fold R and there's the tree for fold L. Okay. So you can think of these things in terms. So some people, if you go to Wikipedia, like see how, well, if you Google fold L, you see how people they draw these trees. Various forms of thinking about fold L in terms of these trees. Okay, so a lot of people they draw the tree for a fold L. If they're trying to analyze a fold L or a fold R, they'll actually draw the tree. Okay, and if you like Wikipedia starts off with these trees for fold R and for fold L. Okay, all right. Notice that they did it. This is thinking of it as an operator, and this is thinking of it as a function. So here they wrote the F, and here they wrote the operator. Because some people like to think of it as a function, some people like to think of it as an operator. And they're using the colon symbol to represent the operator. Okay? So you can think of it in terms of operators or functions. So, okay. So now, so that's a pretty straightforward fold L. Okay, so there's doing a real straightforward one. That's what this one works out to be, that, and this one works out to be that in ML, and it would be that in other languages. Okay, now let's look at this slightly harder one. Okay, give this guy the name. This is F. The initial value is 0. So what this thing's going to do, it's a fold R. So it's going to be F of, I'll call this function F to be able to write out, then I'll think about what it does. So it's F of, okay. Now fold R, we just did it. 0 is the initial value. Well, 1 is the first thing in the list, and 0 is the initial value. See, so 1 is the first item in the list, 0 is the initial value. I apply F to 1, 0. Okay. Now that let me find the formula for fold R on this page. Where did I write it? Oh, up here. Okay, there's the formula for fold R. See, we were doing fold R. There's what it looks. There's what fold R looks like. It works from right to left. Okay, so initial value with 1. Okay, then I'll take 2 and feed that into F with the result of feeding 1 and 0 into F. Okay, so I took 0 and 1 and fed them into F and got back an answer. Then that answer is going to be fed into F again with, oh, I'm sorry, fold R, start with 6 on the right. Yeah, fold R, I start with 6 on the right. So then this one is 5. Okay. Now that result is going to be fed into F with 4. Then that result's going to be fed into F with 3. Okay. Then that's going to be fed into F with 2. Now, it's a little bit tedious to do these things, but the practice in thinking about. And then the last one was that would be fed into F with 1. Okay, so there is, there's this formula here. That's a fold R. Okay, all right, then I can start working my way from inside out. Okay, so start working on what this thing does. So make a copy of it. What does this one do? What's f of 6, 0? So now you look at what the function is. This is 6 and 0. So what does this function do? This function takes in two numbers. If what this is doing is asking if x is an even number. Is x mod 2 equal to 0? So that's just saying, is x an even number? If this is an even number, then add x and y together. If this is an odd number, just give back y. Okay. Now, what is it? Okay, now we have to figure out what this is doing. Okay, the function says, if you give me two numbers and one of them is even, I add them. If you give me two numbers and one of them is odd, I give you back the right one. Okay? Okay. All right. Now, what does that do over here? Here's the number you test whether it's even or odd. If this is even, you add it to that. If this is odd, you just give back that. Then you take that result and you feed it into here. If this is even, you add it to that. If this is odd, you just give back that. Then that is given to here. Can anybody see, real quick, does anybody see what this thing's doing? You give it two numbers. This is a famous example, actually. You give it two numbers. If this one is even, you add that number to the second one. But if this one is odd, you only keep the second number. Now, the second number is the starting value, and it's always the result of this. The result of this function is always the second number. So if this guy's even, you add it in. If this guy's odd, you don't add it in, and that's the result. Does anybody see what it's doing? Six is even, so it gets added to the 0. Then you get back 6. Now 5 is odd. In the odd case, now this is 5, it's odd, so I ignore the x and just return y. Okay, so I get back 6 again. Now 4 is even, so I'm in the even case, so I add 4. Then 3 will be odd. If I'm in the odd case, I don't use the x and just give back the y. So can we see? It's you see what it's doing? Is it summing the list? See, it's adding up the things in the list, but what is it? There's a trick. It's summing the list with a little twist. What's the little trick?
It's summing only the evens?
Yeah, it's taking a list and summing up only the even numbers. It's a really tricky little way to say, add up the even numbers in the list. So add up 6, 4, 2. Okay. Now, now if check it, just go over here real quick. The result was 12, because that's 6 plus 4 is 10, plus 2 is 12. Okay, so it added up the even numbers in the list. Okay, so like if I put a bunch of odd numbers in there, doesn't change the result. If I put a big even number in there, see, it got added into the list. Okay, so it's only adding up the even numbers. Really quirky way to say, take a list of numbers and only sum up the even parts of it. Okay, and if you wanted to sum up the odd parts, you could just change that to a 1, and then you'd be checking if x is an odd number. you added up the odd numbers in the list. So that's 1 plus 3 is 4, plus 5 is 9, 12, 15, 16, 18, 21. Yeah, so it added up the odd numbers. Okay. All right, so fold, you can do amazing things with folds. Folds turn out to be one of the most powerful things in computer science. There's a whole, I think I mentioned once before, there's this whole theory the universality of fold. You can write an amazing amount of code using folds. Okay, there's a sense that a huge number of things, a huge number of functions can be written as a fold. Lots of loops and lots of processes you do on data structures can be written as folds. It turns out to be an amazingly powerful little trick, but not easy. Okay, so yeah, it's kind of a weird trade-off. You can write almost anything in terms of folds, and you can make almost anything unreadable by writing it in terms of folds. But at the same time, once you get used to them, it's much better to write one line of code that's a fold that's complicated than it is to write 10 lines of C++ that's maybe looks to be easier, but could have really subtle bugs in it. So there's a real trade-off to this stuff in the real world of programming. It's something that people spend a lot of time debating. Is it better to write complicated one-liners using fold, or to write more verbose 4 or 5 lines of C or C++, which is really better in the long run? And the world's leaning towards one line of fold versus 5 lines of C++. That's the direction that the world is headed in. One line of fold instead of 5 or 6 lines of C++ or C or Java for that matter. Okay. All right. So we'll do a few more of these next week, and then we'll start talking about ML's data structures. There's a lot here. You could actually spend a long time just talking about this. All this stuff about higher order functions is really deep and can be pretty tricky. And as I just keep saying, be getting more and more important. This is just becoming more and more a part of real programming. Okay, so we'll play with some more of these on Thursday, and then we'll start talking about ML's ability to define data structures. Anybody got any question at the end?
I have a question. It's
Yeah.
not really related to these topics, but about the final. Do we are we gonna have like some sort of like review guide?
Oh yeah,
or
yeah,
anything that you're gonna post?
yeah. I'm gonna try to have that out in another day or two. Yeah, I'm sorry. Yeah, thanks for reminding me. Yeah, there'll be a brief. It's not gonna be a long final. It's gonna be a brief final on ML. So it'll be ask you to read and write short bits of ML. In fact, it'll look a lot like these kind of things. Okay, these are really good problems on thinking about what we learned about ML and functional programming. So actually, the exam will look a lot like these kind of little things we've been doing here. Okay, but yeah, I'll give you a review sheet that says exactly what kinds of things you need to know about ML. And the exam will be, if you've been in the other classes I've had, like operating system, the exam will be the exact same way. It'll be on Brightspace, and you'll download it, and you'll have the whole afternoon and evening to work on it. So the exam will be set up exactly the same way as I did in operating systems and in like last year's classes. Okay, so it'll be set up the exact same way. Okay, okay. So yeah, there'll be review problems for it pretty soon. Okay, other questions? Okay, so look, I'll put these problems up, like, right, I have these I haven't put these up on the website yet. So I'll put these problems up on the website and the solutions that we did today. So I'll put up 2 documents. One document's gonna have just the problems, and the other one will have the ones that we solved today. So I'll put both of those up there. Okay, and then so I'll go ahead and quit there, and we'll do more weird higher order functions on Thursday. Okay, so meet again on Thursday. Bye.